Okay, welcome to the solution to problem of the day that was posted on 8/4. We just needed to get these under our belts because we're getting ready to move into something where we're going to use them. Okay, we want to prove that the wedge product is antisymmetric using these two vectors in summation notation. Now this is very straightforward. So A wedge B, we pull the components out front, we just get EI wedge EJ. Now let's do the opposite, which is B wedge A. So B wedge A. Pull the components out front, we get EJ wedge EI. Remember the rule, when we flip these, we pick up a negative. So now we've got the same wedge product here, right? And the order of these products doesn't matter. So this is the negative of that. Now let's take a look at this. Okay, here I just made up some vectors. There's vector A, vector B, okay? Now I want to wedge A with B. So it'll look like A wedged with B. So I went in a counterclockwise direction, which implies this is a positively oriented plane. Now the way I think of this is the wedge product and the cross product are related, but only in 3 dimensions, okay? So the cross product of A and B looks like that. So it gives a vector that points in this positive direction. Now let's do the opposite. Let's wedge in this direction, B wedged with A, B wedged with A. So I went in a clockwise direction, which implies this oriented plane is negative. So that would be B cross A. And you see, it goes in a negative direction. So that's how I think of these things, okay? If that helps. It helps me. Okay, part B. Prove that the wedge product is distributed, okay? Using these 3 vectors. Now, here was what I was warning you about. When you write this out, here's vector A, and here in parentheses, you're going to add B to C. Well, how do you add vectors using summation notation, okay? Because these are all different indices. We can only add them if J equals K, right? Here's an example. So let's say this is vector A, vector B, has its components and basis vectors. Now when we add these, we say A1 plus B1 goes with basis vector E1, and A2 plus B2 goes with basis vector E2. So you can see these are just summation notations, right? So I can write this as AJ plus BJ equals EJ. That's what we have to do. So here's what we had. Now these are summation notations. We can call them anything we want, right? So we just change these K's to a J, and now we distribute the product, and we get this. So we pull the components out, we get EI wedge EJ. Pull these components out, we get EI wedge EJ. Now, what is that? Well, that's just A wedge B. And what's this? That's just A wedge C. So there's the proof. Okay? One more. Prove that the wedge product is associative. All right? So let's do this side first using these 3 vectors. All right, so A wedge B, here's A wedge B, pull the components out. Here's our wedge product, that's straightforward. Now let's wedge that with C from the right, okay? So once again, we just pull the components out, we distribute the wedge, and we get this. Now let's do the other side. Excuse me. So it looks like this. We pull the components out. Here's our wedge. It's exactly the same as that. Okay, I'll see you later.